So we want to be able to get to understanding inverse matrices, but before we get to that point, we're going to spend some time in this little segment dealing with identity matrices and making sure that we have a good understanding there. One identity matrix we've talked about already, and the other one will be brand new to us here now. So the first thing I want to highlight right here is the identity matrix when we're dealing with the operation of addition, which we've already discussed. So we have that whenever you pick some sort of a matrix, let's say like 1, 2, 3, 4, and then if you add 0, 0, 0, 0 to it, right, then you're going to get the same matrix. And that illustrates the identity property, okay? So specifically, that 0 matrix itself, we call it the additive identity matrix, which again, we give the name capital O for it. And so whenever you see the dimensions there, that's going to specify how many dimensions it has. And so, you know, if we were to do A plus the 0 matrix, of course, that's just going to equal A, which in that case would just be 4, 1, negative 5, negative 2. And the same thing would be true if you reversed it, right? So I do want to note that the additive identity matrix is what is also known as the 0 matrix because it contains all zeros inside of it, right? And then if you think logically about what would happen right here if you were to take a matrix A and multiply it with a 0 matrix, so that's like 4, 1, negative 5, negative 2, and then multiply it with the 0 matrix, that's a 2 by 2, think about what would happen there, right? You do 4 times 0 and then 1 times 0 and add that together, well, you're going to get a 0 and then a 0 and then a 0, right? So it does turn out that if you do matrix multiplication and you multiply it with a 0 matrix, like you're just going to get zeros. And the same thing would be true right here, that you just get the 2 by 2 0 matrix there kind of as an answer. So that's just kind of some recap in terms of reminding ourselves that capital O is the 0 matrix and some terminology there. So now we're going to transition to the another operation of multiplication and talk about what we deal with the identity property there. So if we're trying to deal with the identity property, but now with multiplication, basically what that means is if I were to try to take a matrix that I'm just going to make up here, so 7, 5, negative 8, negative 2, and then multiply it with something, and I want this to illustrate the identity property. The identity property means you want to end up with the same result after you perform the operation. So the question at this point would be, well then, what should that matrix need to be if we're trying to multiply matrices and get the same answer? So you might think and guess, like, well, whenever we multiply by 1 with numbers, right, we get the same answer, so maybe this matrix should be all ones, right? And that's something that we could check. So if we then multiply these two matrices together and we start with 7 times 1 is 7 and 5 times 1 is 5, then we do 7 plus 5, which is going to give us 12, and so we should get a 12 there, which isn't the same as the 7, which means we're not getting the same answer, which means this isn't showing the identity property. So that matrix right there can't be the multiplicative identity then, not just all ones. So it turns out that actually what you need is you need a matrix like this, and that would be considered the multiplicative identity matrix. So any multiplicative identity matrix will always contain ones in the main diagonal and zeros everywhere else. So we actually give that matrix a name. We call it capital I whenever we're dealing with a multiplicative identity matrix. So kind of some info down here. So the multiplicative identity matrix, it does need to be a square matrix. So by being a square, that means that it needs to have the same number of rows as it does columns. So when we call it I, oftentimes we'll put a subscript number right there, which will tell you the number of rows or the number of columns. Of course, we only need to put one number since it's always square. So if it was like a 5, you would know that both the rows and columns are 5 in many, right? So like I2 would look like this. It would be 1, 1, and then zeros everywhere else. Or the identity matrix that's the 3 by 3 would be I3. So you would fill up the entire main diagonal with ones, and then you do zeros everywhere else. And then just one more. So if you had the 4 by 4 identity matrix, you'd have 1, 1, 1, 1, and then 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. right? So those would be the identity matrices. So when you multiply with those particular matrices, then you're going to get the matrix that you're multiplying with the identity matrix kind of as your answer again. So it does turn out with this problem right here, your answer will be 4, 1, -5, -2, because you are multiplying with an identity matrix that's got the zeros everywhere else in the ones in the main diagonal. If you want to work through that matrix multiplication, you certainly can, but it does end up working. And the same thing would be true if you put the identity matrix first. You definitely do get the 4, 1, -5, -2 kind of as your answer there. So that's just kind of summarized generally here that whenever you multiply with an identity matrix, as long as the dimensions are as you need them to be, right? Because when you're multiplying matrices, you need the number of columns in the first matrix to be equal to the number of rows in the second matrix. So yeah, as long as that stuff all kind of lines up, then whenever you multiply with that identity matrix I, then you'll just keep the matrix kind of the same. So I want to kind of help build it just a little bit more with some of that new knowledge about this I matrix or this identity matrix with a particular problem here. So it says to let I3 be the 3 by 3 multiplicative identity matrix, and then also to let M be that matrix that has all those numbers right there. So if M equals 4n minus 7i, find n11 plus n22 times n33. Okay, so this is what we're asked to find right here, right? So we want to find n11 plus n22 times n33. So what you'll kind of want to notice about that is that those are lowercase letters here, and so those are going to be specific elements inside of a matrix where the matrix is going to be called capital N, right? So we're going to need to know what elements are inside of matrix N, and we don't have N, but N is kind of involved there with matrix M. So we're going to have to do some solving to kind of find what this matrix N is. So kind of setting up based on that equation right there, so it does say that M, so just kind of copying M, is equal to 4 times whatever n is, which we don't know, so we'll leave it as n, minus 7 times I. And so knowing what I is really important. It does say that I is the multiplicative identity matrix, so you have to know that that has to be 1, 1, 1, and 0, 0, 0, 0, 0, 0 to be the 3 by 3 identity matrix. So now, which is kind of a matter of solving for the matrix N, so we can get the numbers that we need from N, of course, right? So, of course, that -7 is going to multiply to all of the numbers inside of that matrix, which when it multiplies with the 1s will turn to -7, and when it multiplies to the 0s will remain 0s. So we're going to get, I'm just going to erase that and just kind of rewrite that this is going to be -7, 0, 0, 0, -7, 0, 0, 0, -7, right? But I guess it's not subtracted anymore because now we're going to add since we distributed the negative. So in order to solve for n, we're going to want to undo the adding of that and then divide by 4. So basically, we're going to need to subtract -7 or really just add 7 to both sides, right? So if you add 7, 7, 7, 0, 0, 0, 0, 0, 0, that matrix, then you're going to add that same matrix to the other side. So it's really just going to add 7s to the main diagonal numbers in the matrix on the left side. So I'm just going to erase that, assuming we canceled, and then I'm going to add 7 to that to make that -12, and that's going to become +4, and that's going to become 24 when you add 7s to those. So those are the only numbers that would change, and then we just need to divide everything by 4, and then we've solved for n. So when you divide all these numbers by 4, you get -3, -2, 1/4, 0, 1, 1.5, -half, -1.75, and 6 right there. So now we finally got that matrix that's called capital N, and so what we want to find is we want to find that, where we take n11 plus n22 times n33. So 1, 1 means what's the number in the first row and in the first column? Well, that would be this number right here, -3. So this is going to be -3 plus And then 2, 2 would be that number right there, the 1 times the 6, because that's in the third row, third column. So when you evaluate that expression, of course, you got to follow order of operations. You actually have to do the multiplying first, so 1 times 6, and then you can add the negative 3 to the 6, and that's going to give you an answer of 3. So that right there actually answers the question that was asked, to be able to find the value of that expression there.